This is how this works, and it's really nice to know this. This whole class, you learned everything about the linear stuff already. Everything you know is good. Everything from now, you spend a little bit of time. You probably spent 1 or 2 lessons learning the angular stuff. There are combinations they have to go.
Yeah.
So in the linear, you have the position. Sometimes people are going to write S, right? Position. I use S because whatever. So you have S. Then you have velocity, which is V. V is equal to ds dt. And then, of course, it's a vector, so you technically need
derivative of position with respect to time.
Yes. Now, in non-derivative form, you just write it as delta S over delta T. Then you have accel.
The change in that.
Acceleration is equal to the derivative of V, which you could write as delta V over delta T if it's not a if you don't need to use calculus, right?
Okay.
But then, of course, that could be tangential or that could be regular. So then I always like to put the normal.
Yeah.
The normal, if you're working on circular motion, normal tangential, then the normal would be V squared over R, and that's just it. Okay.
Yeah.
So that's all of that. Then what you're going to do is in the next month or two, probably over the next month, you're going to learn how to do it for momentum, and you're going to know how to do it for force. And you're going to actually I'll do it. Momentum is seen as L, and it's equal to.
Yeah, I know that one. I think.
Dope.
I know we did like impulse, momentum, and like force, and then like potential, and then like understanding like work and stuff like that.
Yeah.
But, like, I never understood like the derivatives because I really didn't do I really didn't focus on calculus, and so it just always messed me up trying to find it. And it's like always a puzzle piece that she puts into the problems, and then it'll just mess up everything else I'm trying to understand.
It's not hard at all. This is all you need to do. This is what I want you to think of. For this, you use the derivative, use calculus. If an equation is given, if like an actual position equation is given. So if an equation is given, now you can do it for position, velocity, or acceleration. So if they give you an equation for either of those, you got to use calculus. So if she says, oh yeah, the function is given as st equals 3t squared plus 4. What's the velocity and acceleration? Then you got to be able to use this and then do your derivatives.
Yeah.
If she gives you to you where velocity is 6t plus 7, whatever, then what you're going to have to do is you're going to have to derive for this, and you're going to have to integrate for this with the initial conditions. Integrate at initials. Make some sense? And then if it's the acceleration, then you're just going to integrate 2 times based on the initial conditions. Okay?
Yeah.
From there, that's just pure motion stuff. Once you figured out that, then it's plug and chug. Then it goes right back to plugging and chugging. Okay? So once you can pull out the position, velocity, and acceleration. So that calculus is literally just to set up position, velocity, acceleration. So the calculus is just to go back and forth between these 3 terms. That's all the calculus does. Okay?
Yeah.
So that's it. Once you get that part, everything else is as you know how to do it. Okay? So everything else from there to be like, oh, all right, so if that's the velocity, then I got to do a free body diagram or work energy based on velocity. You do work energy based on velocity. Yeah. You do impulse momentum based on the velocity and time. You do and you do a free body diagram based on acceleration, because each one of those uses different variables.
Yeah.
Okay.
Like motion diagrams.
Yeah, exactly. So from there, it's easy enough to do the angular. You have angular position. Angular position is oftentimes given by theta, and you have to know that S equals theta times R. Yeah. Okay, so that's how you convert from one to another. Then you have angular velocity, which is W, and you got to know that V equals W times R. And obviously, if you use the traditional if you use this equation like as a reference, then what's going to happen is you'll get that W equals d theta dt, because the arm is not changing. Okay, and then last but not least, you get regular acceleration, tangential acceleration, excuse me, converts into alpha, which is dw dt. And you have to say tangential acceleration specifically is alpha times r, okay?
Mm-hmm.
And then for the normal acceleration, it stays as a normal acceleration. It actually, normal acceleration is a linear term and an angular term. And that's just going to be equal to w squared times r.
Mm-hmm.
And that's your conversion. And you're just using this right here. That's
Yeah,
what you're
I feel
using
like
to get
there's one that's missing. Cause isn't there one that's like the relation, like that relationship equation for the linear, and then there's a relationship equation for the angular. You know what I mean? Like it's a times the derivative of position or something like that, ds or something. I don't know.
Oh, all
Does that
right.
make sense?
So
That's
yeah,
the
yeah,
one
yeah,
that's
yeah.
confusing.
That's the one that does oh man, I don't even think I remember it anymore. That's this one. A is equal to dv dt. It's also equal to d squared s, or dt, so it's ds squared. ds
Mm-hmm.
squared dt squared. And then the last one is you get an integral. It's going to be like a equals shit, how's it go? VDS. I think it's like that. I think it's like that. Let me look it
Yeah,
up for you.
it's like it's yeah, you can. I think
I know exactly which one you're talking about. I'm gonna get the exact one for you real quick. Um, Acceleration in terms of position and velocity.
yeah, acceleration ADS equals VDV
There you
exactly.
go.
So it's like
ADS
we
equals
had that right
VDV.
there.
Almost. I almost got it right. And so that right there, what that really is that's a relationship. So that's not an equal. You've literally combined these two equations. I don't remember how they did it. I'm not gonna lie. I just know it was awesome. ADS equals VDV. Now that one could be really wonky. That one could be really wonky.
That's what I'm saying. That one confuses me because what DS is just the what is DS and what is DV? Like, or is that
Easy.
just literally the derivative of velocity and the derivative of position?
All right. So this is not the derivative of velocity and position. It means you're going to do. It means in reference to.
Mm-hmm.
So remember look at it like this. ds dt is the derivative of position
Mm-hmm.
with respect to time.
Mm-hmm.
So the derivative of the top guy and the bottom guy is your reference. The whole with respect to, that's what the bottom dt
Mm-hmm.
represents. It's your reference. So what this means is we're going to have to take the integral because that's how that works. It means you're going to integrate a with respect to s. Integrate
Okay.
a with respect to s. Now, the only way you can do that is like this. Here's what it looks like. If a is given in terms of time, so let's say a was 3t, then the integral of a ds is literally going to be the integral of 3t ds. T is going to work as a constant. I put a dt, my bad. It's
Mm-hmm.
supposed to be ds. T is going to work like a constant. So what's going to happen is you're going to have 3t integral of ds, which is going to give you 3ts equals a, or that's going to equal velocity. No one's going to do that. No one does this. That's because what you've done is you've just introduced two variables and you just made it a pain in the butt. So that's not the way to do it. That's right, but that's not the way that it's going to be expressed. The way it's going to be expressed is like this. And this how you, oh man, now I see exactly what you mean. Now it comes perfectly together. What this does is you need a in terms of s. So literally,
Mm-hmm.
you can have a in terms of t, or you can have a in terms of s. If a is in terms of t, my bad, hold on. If a is in terms of t, come on now. If
Yeah.
a is in terms of t, then you're going to use these guys, right?
Mm-hmm.
If a is in terms of s, then you're going to use this guy. So what happens is, let's say a was equal to 3s squared plus 2s plus 4. ADS is now going to be the integral of 3 s squared plus 2s plus 4 ds, which is a very, very realizable integral. Make some sense?
Mm-hmm.
And so that you just do your regular integral, you're going to get your 6s plus your, oh, hold on. It's not 6s. It's, I did the derivative by mistake. It'll be 3 over 3, which is s cubed plus s squared plus 4s. And then you have to use your bounds, a1 to a2, and that's going to be velocity. You see what I'm saying?
Mm-hmm.
So the whole idea behind that, because now I see exactly what you're talking about. It's literally a difference in how s is present, in how acceleration is presented. This one is the time representation, and this one is the position representation, and they can give you either one. So they could say the acceleration based on position, and it'll be a sub s. Acceleration in terms of, as a function of, that's what it is, as a function of. And so you can have as a function of time, which is the most common one. If you have a with respect to time, then bam, you use the time representations. If you have a with respect to position, then you're going to use the funky positional version. Make some sense?
Mm-hmm.
Now what happens is, if you use the funky positional version, then that's actually going to be equal to, I messed up. I wasn't supposed to put V. I was supposed to put this. It's supposed to be VDV. That's actually equal to VDV. VDV is not a real thing. VDV is just an idea.
Another relationship.
Yeah, it's just another piece of an understanding. So once you found that ADS, you have equals VDV, and you're good. Okay. Now, if you know velocity at that moment, let's say you know velocity is going to be constant, right? Then you plug in the 3, and you're going to have VDV. It's just going to be 3v from v1 to v2. That's how that will be written, and that is what will go there. Okay, and that's how you set up the relationship. And so now you have acceleration, velocity, and position all in one equation without time. And so that's what that relationship is supposed to do. But that really only works when they don't give you anything about time. They just give you position, velocity, and acceleration all as specific at the same time, but you don't need time anymore because now they're all intercorrelated. So that's how that would end up working out. Okay.
Okay.
Does that make some sense?
Totally.
That right there does correlate. You do, of course, have a version where you could write it in the angular, and that would just be alpha d theta equals w dw. Like you can do that, but now you understand that it's just about.
She does that too.
Of course she does, because why not? Whatever. That's some jerk move, but now you understand that it's all based on how the acceleration is presented. So this would be if alpha is given as time. I don't know what just happened. If alpha is given as time,
I kind of get it. You just sub it out. You just sub it out.
Yep. It's just a matter of understanding. Oh, she gave it to me in terms of time. I got to use alpha equals dw dt. Oh, she gave me alpha in terms of position. I got to use a position relationship.
Yeah.